There is a rule called Zaitsev rule. Now, in reactions where you make alkenes, the alkene that's more substituted tends to be the major alkene, or the major product, so to speak. But so let's talk about substitution of alkenes before we narrow down on Zaitsev rule. So substitution of alkenes. So I'm gonna draw them right down here. So let's say you have carbon containing substituents. I'm gonna call them R groups. Okay. If you have 4 carbons directly bonded to the double bond, this is called tetra substituted. So like a tetra pack. So this is tetra substituted. It's gonna be more stable than one that only has 3 carbons directly bonded to the alkene. So let's say you have 3 carbons directly bonded to the alkene. This is called tri-substituted because there is 3 carbons directly bonded to the alkene. Substituted. And then that's gonna be more stable than one that has 2 carbons directly bonded to the alkene. And you see these 2 carbons are opposite, so we call this trans, but it's gonna be di-substituted. The trans is more stable than the cis, where the carbon substituents are on the same side. So this is cis. Cis means same side. So the cis isomer of the di-substituted. Why do you think the cis isomer is less stable than the trans di-substituted isomer? The reason is if you have carbons here, then you must be having hydrogens on them, then there's gonna be crowding. That's why the cis isomer is more stable than the trans. And of course now you also have this cis is said to be approximately equal in stability to where you have the carbon groups sharing one of the sp2s. But again, the mono substituted with only 1 carbon group, mono substituted, will be less stable than the dice in theory, and then the mono will be more stable than the regular reference ethene, where there's no carbons attached to these sp2 carbons. So that's Zaitsev rule, stability based on substitution. So Zaitsev rule states that the most highly substituted alkene will most likely be the major one, but you also consider sterics. Like here, both these 2 alkenes are di-substituted, but one is trans, the other one is cis. The cis is crowded, the trans has the B groups opposite. So in this reaction where you're making double bonds, the double bonds can end up anywhere. Hence this term called Regio selectivity. So the double bond can go anywhere. As much as you're looking at the substitution, whether it's tetra, tri, or di, or mono, as much as you're looking at the substitution, you also need to look at sterics. So consider this reaction. You do have an alkoxide here. Remember, alkoxide is RO minus. Those tend to be strong bases and also strong nucleophiles. We talked about that in an earlier lecture. So if you're going to think elimination, then we are considering the alkoxide as a base. If it's a strong base, then you are thinking E2. Strong bases usually do E2 or Sn2. But looking at the products that are shown here, we are doing elimination because we are making pi bonds. So we no longer think of Sn2, we think E2, and we use this as a base because elimination uses bases. Now on your substrate, you have to identify the neighboring beta carbons that's where you'll pull out the beta hydrogens. So this base can come and take out this hydrogen, which is 180 degrees. The hydrogen is 180 degrees orientation to the leaving group. That's called the anti-periplanar rule. We discussed that in a previous lecture. So if you do this reaction, then you're going to get a double bond within the molecule, and that gives you this this product right here in 60%. Now, if you take the same molecule, but this time you're taking out a hydrogen from the other beta carbon, you're using your base. I'm not going to show the hydrogens. I'm just gonna show the line angle. Use this as a base to take out the beta hydrogen and make a double bond, and this falls off. That's how you end up forming this product. Okay, notice that this product right here is di-substituted. Di-substituted. Why? There are two carbons directly attached to the sp2 carbons, but it's also trans because those two carbons are up and down. They're up and down, right? Up and down, up and down, whichever way you look at it. Okay, so it's trans. The carbons are pointed opposite way. Then this one right here, it's mono. This is mono substituted. So because it's mono substituted, it's gonna be less stable than the di-substituted. This one right here can be formed this way. So let's say you have your molecule like this. We say the sigma bond can rotate, so we are rotating this carbon right here. We are rotating this carbon here. If you do your rotation, you're gonna end up with the Br up and then that down. So let's say we take off, let's say the base takes off this hydrogen on the neighboring beta carbon. If you take out that, maybe make a double bond, and that goes. I know I've not drawn it 180 degrees apart, but for purposes of showing you where this comes from, this is what would happen, and therefore you get this molecule. Notice the backbone of the carbon, the metals are on the same side, so this is cis alkene, but it's di-substituted. Now notice that the cis and the trans, both of them are di-substituted, but because of sterics, then the trans is formed in a greater amount of yield compared to the cis, and the cis apparently is formed in equal yield compared to the mono. So that's what Zaitsev rule states. In reactions where you're making double bonds, the more substituted double bond will be the major, especially if the base is small. Okay, if the base is small, that's gonna be major. All right, so I hope that's clear. Next, these are just Newman projections showing you the various orientations on how to get these products. I'm not gonna discuss those. It might be a little bit confusing for you. So that was E2. This is E2 because you can see the reaction is concerted. We are pushing the mechanism arrows down, 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 down at once. No formation of carbocation. But now for E1, you will have to form a carbocation because E1 is unimolecular. Only one of the reactant determines the rate, right? So in that reactant happens to be the alkyl halide. So for example, this is an alkyl group. Assume this is a chlorine or a bromine. You first have to make a carbocation. Sn1 and E1, both of them have to form a carbocation before the nucleophile attacks. We did that in the previous lecture. So the leaving group is gone. So this guy could be Cl minus, Br minus. The leaving group is gone. So now you have a carbocation, and the carbocation happens to be tertiary, so it's stable. Remember the stability of carbocations. Tertiary is more stable than secondary, more stable than primary. It's tertiary because the carbon bearing the plus charge is bonded to 3 other carbons. Okay, now you have now 2 options. Either you go Sn1 or E1. If you go Sn1, then you're gonna need a nucleophile. Okay, so let's assume here the nucleophile. Let's assume here the nucleophile is OH minus. So if OH minus attacks the carbocation, then you're gonna get the OH right there. Okay, which reaction is that? You started with a leaving group, a chlorine or a bromine, you put an OH, you substituted, that's Sn1. The OH minus can decide to play the role of a base, in which case we are thinking E1 or E2. Now, if it were E2, really we don't need a strong base, we need a weak base. But anyway, because we have a generic nucleophile here with a negative charge, let me use OH minus. So for E2, what you'll do, for E1, sorry, what you'll do, you're gonna need the same carbocation, but you will pull out, either this beta hydrogen or the beta hydrogen that's here. Now remember this rule: the more substituted alkene will be the major. So we have to take out a hydrogen from a more substituted neighboring carbon to get the more substituted alkene, and that's how you get that. So again, you have the option of taking out that hydrogen or one of these hydrogens right there. Okay, so to get the more stable, I'd rather take this out because this is sitting on a more substituted beta carbon rather than that. Make a double bond, and that's how you get this. So this will be your E1 product, and this will be your Sn1 product. And it's a Z-self product because it's more substituted, according to Weiss's Z-self rule. Because if you take the same carbocation and take out the other hydrogen, so let's say OH minus took out this hydrogen, you are going to form this double bond. Sorry, not that one. You will be forming this double bond right here. And this one only has 2 carbons attached to the sp2 carbon. So this is disubstituted, while this one right here is tetra substituted. So that's why we are only showing this one, because that's gonna be the major Z-self product from E1. All right, so moving on again, giving you more examples. So like I said, E1 will use weak bases, not strong bases. So and weak bases most likely gonna be neutral. So E1 goes with weak base. Because it's elimination, we call it a base. Sn1 will go with weak nucleophile because substitution needs nucleophiles. So you look here, you see you have an alcohol. Alcohols are neutral, they are not negatively charged, right? They're not negatively charged, so they are weak bases. Now, this substrate here is tertiary, so Sn2 has no chance because the backside is hindered. So we'll think E1 and Sn1. So this can go Sn1 or E1 just based on this structure is a weak base. This reagent ethanol is a weak base. If it was an ethoxide, that's a strong base, we'll think E2 because E2 requires strong bases. So Sn1 and E1, both of them lead to formation of a carbocation. That has to be formed first. So the carbocation is gone. The carbocation is formed, sorry. Now, if you are to think Sn1, then this is the product that you'll form, because as you can see, this group came by. So what you'll do for Sn1, you will take your ethanol. Okay, let me change a pen right here. So you will take your ethanol and then use the lone pair to attack the C+. That way you're gonna end up with a plus charge on the oxygen. Okay, and a bond to the where the carbocation was. But that's not the final product. So you need another molecule of ethanol. Okay, you'll need another molecule of ethanol. Let's just use this one so I don't draw again, to take out this hydrogen to neutralize the oxygen, because organic molecules like to be neutral. That's how you get the product here from Sn1. Now from E1, you're gonna use the same carbocation intermediate. That's why Sn1 and E1 compete, because they form the same thing. And then you're looking for the Z-self product. To find the Z-self product, draw the possible beta hydrogens and then choose to take out the beta hydrogen sitting on a more substituted beta carbon, which happens to be this one, not these two. This is more substituted carbon because bonded to more carbons than these two carbons. Okay, so that's the beta carbon, that's a beta hydrogen. So we take it out and then use its bond to make a double bond. You're gonna end up with this. The plus charge will go because you've just dumped electrons in between there. So this is the Z-self product. To get this one, you do the same thing, but this time around, you're gonna take out the wrong hydrogen, the wrong beta hydrogen. So that's a neighboring carbon, okay, in your carbocation. So to get the product here, you use again a second molecule of ethanol as a base, as a weak base. Take out the hydrogen, use the bond to make a pi bond, you get this. So you see this one has two alkyl groups out of the alkene. So this is disubstituted and terminal. It's terminal because those alkyl groups are sharing the same sp2 carbon at the end. And this one has 3 carbons popping out of the double bond. So this one is tri-substituted. But it so happens that the E1 products, which make double bonds, are the minor products, because 30 plus 6 is 36. But the Sn1 is winning. Why so? Because this is a weak base. It's not strong enough to take out those hydrogens. So the ethanol would rather attack the positive center rather than playing the role of a base. It plays the role of a nucleophile. That's why Sn1 wins over E1 most of the time. Here we used a weak base. Down here you're using strong base here, which also happens to be a strong nucleophile. Now if it's a strong nucleophile, then one would think Sn2 should be happening, but Sn2 will not happen because this substrate right here, we said is tertiary, the backside is crowded, the nucleophile cannot approach from the back to attack this carbon right here by Sn2. So instead, we're going to still follow Sn1 to show how we are making the substitution product. So in that case, you lose the bromine, you make your carbocation, and then your ethoxide, it's an ethoxide because there's 2 carbons, eth oxide. So your ethoxide attacks the plus sign, and that's how you get this product. And it's by Sn1 because Sn2 could not happen, which we expected because it's a strong nucleophile. It couldn't happen because the backside is crowded. So that's how you make your Sn1 product, but it's in very less amount again because of crowding and because this is a strong nucleophile, strong base. So instead of playing the role of a nucleophile, it's going to play the role mostly of a base. So you will take your substrate, okay, it's a strong base, so we expect, since it's a strong base, we expect E2. E1 works with weak bases, so we expect E2. So in that case, what do? Again, elimination requires deprotonation of a beta hydrogen sitting on a neighboring beta carbon, neighboring to the carbon bearing the leaving group, which we call alpha. So now we take the strong base, to remove the beta hydrogen. The reaction is concerted because it's E2. That's how you get this product. Okay, the Br falls off, you make a double bond, you make that product. But again, the base can forget and take out the wrong beta hydrogen. So probably it takes out this hydrogen. So you make a double bond and the bromine falls off. Bromine falls off by that mechanism. That's how you get this product. In this case, the elimination products are the major 93%, all because you used a strong base. E2 will win. Now, generally, how can we compare substitution products and elimination products? We start by looking at alkyl halides. Tertiary alkyl halides are hindered on the back side, so you don't expect Sn2 on tertiary alkyl halides. You only expect mostly Sn1. Sometimes you can do E1 or E2, like we did here. We did E2 on a tertiary. Okay, so now, we also did E1 on the tertiary. That's how we showed the ZSF product. So now let's do more examples. So looking at water, it's gonna be protic. If it's protic, that's another reason why Sn2 will not happen. Remember I said the first reason is because this alkyl halide is tertiary. The carbon bearing the leaving group is bonded to 3 other carbons. So the backside is crowded. You don't expect the nucleophile to attack. The second reason is that the water here is protic. You have the hydrogen bonded to oxygen. That's what makes it protic. Okay, so this is neutral, so it's gonna play the role of a weak base or a weak nucleophile. What does that mean? You either have Sn1 happening or you have E1 happening, right? Now, if you take it to be Sn1 or E1, either way, you have to form a carbocation first, because that's what happens for both Sn1 and E1. Then from there, you either gonna go Sn1 to substitute the chloride for OH, or E1 to create a double bond from the carbocation. So now let's flow and show Sn1. So you attack the C+. Okay. So you get the water there. Let's see. So you get the oxygen, the plus sign on it, the water attached where the plus sign was on the carbon. So now the oxygen is bearing the plus. But again, organic molecules don't like being charged. So another molecule of water will come to take away the hydrogen and use the 2 electrons that makes the bond to neutralize the plus charge. All right. So that's how you get your OH, by removing the extra hydrogen proton transfer process happening right there. So again, the water attacks the carbocation, the water is attached, remove the extra proton by proton transfer, you get your OH, the second hydrogen is pulled out. So that's substitution, because the Cl now is replaced by OH. Now, if you want to get the elimination, you simply take the same carbocation intermediate, and then now the water is not going to be used as a nucleophile, it's going to be used as a base. So you take out one of the beta hydrogens and then use its bond to make a double bond. You're going to get that structure. Of course, it would have looked like this, but if you rotate it, it's the same thing as that. So again, Sn1 is winning here because water is not a strong base. It's not strong enough. Water, it's not strong enough to take out a beta hydrogen. It needs a lot of energy. So that's why Sn1 will win. Here you have a strong base and you have strong nucleophile. You know, strong base can play the role of a nucleophile. So again, Sn2 will not happen because the nucleophile cannot approach from the backside. Well, it's sterically hindered. That process won't happen. So instead of Sn2, we're going to take the alternative, which is Sn1. You get your carbocation intermediate, Cl fell off. Now at that point, your nucleophile comes in. And that's why these reactions are unimolecular. Only one molecule determines the rate because that step is slow, and that's how you form your carbocation before the nucleophile shows up to play role. So when the OH minus attacks, in this case playing the role of a nucleophile, you're gonna make this product by Sn1. The product is least expected to form. The yield will most likely be less than 1%. Very low yield. Why? Again, because this is a strong base. Just like here we said, Sn1 will not show up as much because you're using a strong base. Okay, strong bases tend to be favored with tertiary substrate for elimination. Okay, so now here we use the same molecule, but because this is a strong base, we're not gonna go E1. We're going to go E2 because strong bases do E2. OH minus a strong base, there's a negative charge on the oxygen making it a strong base. So you do that, you drop off the bond after taking out the hydrogen, and this falls off. The reaction is concerted. You're gonna make this product. So these two methods, you know, here you have two hydrogens. That was the third methyl group. You took out one hydrogen, you're left with two hydrogens, which are these two hydrogens, and then you make a double bond. Okay, so E2 will exclusively be made in quantitative, almost 100% yield. So you see how you can reason substitution versus elimination. You have to look at what's given on the arrow, determine whether it's strong base, strong nucleophile, or weak base, weak nucleophile, and then you know whether you're going E1 or E2, Sn1 or Sn2. And then also look at the substrate, make sure you understand it's tertiary, secondary, or primary. Tertiary substrates never do Sn2. That's why on this slide you don't see Sn2. So what about secondary alkyl Those can do all. Secondary alkyl can do all. So if you have a weak nucleophile, you're looking at Sn1. If you have a strong base, you're looking at most likely E2. If you want Sn1 versus Sn2, then use Protic solvent because that disfavors Sn2. If you want Sn2, use a Protic solvent. To refresh your mind, Protic solvents are those which have somewhere in their structure OH or NH or HF. So, for example, H2O, you do have OH in the structure. For example, ammonia, you have NH. Acetic acid, you have OH. Those are protic. They are protic because you have the hydrogens bonded to these specific electronegative elements. Aprotic will include nail polish remover, we call it acetone, or dimethylformamide, which is my favorite for these reactions in the lab. DMF, dimethylformamide, it's an amide, or dimethyl sulfoxide, which most biologists like. DMS, or they like it for cell studies. So none of these have hydrogens directly bonded to oxygen, so they are aprotic. These guys are examples of aprotic solvents. Aprotic solvents will foster Sn2. Protic solvents will foster or help Sn1. Now, for examples of secondary alkyl we're gonna use the 2-chloropropane. You see the carbon bearing the leaving group is bonded to two other carbons. So this is secondary, this is secondary, this is secondary. But what determines the product you get is the reagent you're given. Here you're given methyl sulfide. Okay, this is negatively charged, so I expect it to be a strong nucleophile. And because sulfur is very electronegative than sulfur is more electron pulling than oxygen, then I don't expect it to be a strong base. So I expect only Sn2 to happen because strong nucleophiles favor Sn2. So, and now this is secondary. So we said secondary alkyl halides can do Sn1, Sn2, E1, or E2. What dictates what happens is what you're given on the arrow or what else you're given in addition to your alkyl halide. All right, so it's a strong nucleophile. So it's going to do a back attack concerted reaction, no carbocation, because you have Sn2 happening, not Sn1, which would have formed carbocation intermediate. You get that product. This is just the CH3. So this is the part that's just been added in substitution for the Cl. Here you have a weak nucleophile. You see, it's just an alcohol. Alcohols are weak nucleophiles, weak bases. So you can use it as a weak nucleophile or a weak base. If you use it as a weak base, then you get E1. If you use it as a weak nucleophile, then you get Sn1. It could go either or because, again, the rate determining step is formation of carbocation for both E1 and E2, for both E1 and Sn1, sorry. Both Sn1 and E1 form carbocations. So we use the methanol now as a nucleophile for Sn1 to attack the positive center. So you get OH and your CH3 that came with the methanol and a plus sign on the oxygen. Now to get this product, you need CH3OH, which will definitely take out the hydrogen and then you neutralize the oxygen. So that's how you get your Sn1 product. To get the E1 product, you have to pull out a beta hydrogen sitting on a beta carbon. So you'll take methanol, okay, to pull out that hydrogen, make a double bond, you get this product which is from E1 because that's a weak base. If you have a strong base, which in turn is a strong nucleophile because of the negative charge, again you can do Sn2, assuming it's playing the role of a strong nucleophile. If it's playing the role of a strong nucleophile, you do substitution. Substitution requires nucleophiles. The reaction is concerted, you get Sn2 product like that. But because again it's a strong base and this guy is secondary, I would expect again E2 to be the major, where you will use your strong base to take out the hydrogen. So I know you will want to ask me, how do you know again E2 will win over Sn2? E2 will always win if you have a strong base, okay? If you have a strong base and your substrate is secondary or tertiary, E2 will win. If it's a strong base and you have a primary alkyl halide, Sn2 will win, which is what we're about to do right now. So for primary alkyl halides, like this guy, you only have one R group bonded to the carbon bearing the leaving group. So this is primary. Ethoxide is a strong base. It's an RO negative group, right? So it's a strong base. Strong bases tends to be strong nucleophiles. With primary substrates, Sn2 will win. If you have secondary substrate with a strong base, E2 will win. It's a major. If you have a tertiary substrate, here, tertiary substrate with a strong base, E2 wins. So again, E2 wins whenever you have strong base, strong nucleophile, whenever you have tertiary or secondary alkyl substrate. That's the only time. But when you have a primary substrate with a strong base, strong nucleophile, then you expect Sn2 to win over E2. Let me show you how E2 will form. So you will take your beta hydrogen and then take your strong base, pull out the beta hydrogen, make a double bond, and this leaves. Both Sn2 and E2 are concerted. Remember here, Sn2 would attack from the back. So this leaves, and that's how you make this product right here. And then for E2, you pull out a hydrogen because you have a strong base. You pull out a hydrogen, make a double bond that leaves. Now, the ethoxide definitely is a small, strong base, right? It's small. You see the size? It's small but strong. What if you have a bulky one? What if you have a bulky base like tert butoxide where you have all these CH3s right here bound onto a carbon, and then you have an O negative. So this is bulky. Bulky means it's huge in size, which means it has sterics. It's sterically hindered. So if you have a bulky base, bulky strong base, it's not going to be a strong nucleophile because of the size. So you forget about Sn2. You know, we said Sn2 always competes with E2 because most strong bases are strong nucleophiles. But now this base that we have here is bulky. It's huge. It's bulky. Okay, it's bulky. So it's not going to play the role of a nucleophile here because Sn2 doesn't like bulkiness and stericness, if that's correct English. So Sn2 will not happen because this guy is huge. So instead of Sn2, which would have given us this structure, let me modify, this is a typo. Sn2 will have given us this structure. Instead of Sn2 happening, most favored will be E2 because, again, of the size of what would have been a nucleophile. So you take your tert butoxide and then take out this hydrogen to make a double bond, and this leaves. That's how you make this product. E2 wins in this case because this guy is huge. Take note of that because I'm going to test you on that. All right, so that makes or marks the end of chapter 6, which will be the last chapter to be tested on the exam 2. Exam 2 will cover chapter 4, which was not covered in exam 1. It's gonna cover chapter 5 and now chapter 6. So practice using your homework questions and the suggested end of chapter questions that I always post under the video links. The exam is on Wednesday, July 1st, 12:30.